Hi, I'm Antonio, and in this video we are going to discuss how to plot these LMI sets we described in previous videos and which kind of problems we may be able to solve with them. So, let us first discuss the plotting code. But let me first outline the basic idea, which is that my code will require a center. I mean, it's a draft stuff. I mean, maybe I should have computed the analytic center first and plotting, but okay. From some center, it will generate a ray in some direction, and it will compute the farthest point in this direction, and if I execute the so-called two-sided thing, the farthest point in the opposite direction. Then I will make a lot of rays surrounding everything, so I get these little blue dots you can see on screen, and then I will compute a convex fold to sort them and plot the red line. Of course, the two-sided option is not needed if the center is inside the shape, but for strange shapes in which I don't really know what I am drawing, maybe if I set the center outside the shape, then my ray will compute the maximum scaling and the minimum scaling so that LMIs are feasible. Then these things will be in the interior of the LMI set. So this is the basic idea. And how is it done in MATLAB? Well, let's quickly see that thing, but it's not really that important if you understood the ray stuff, so you may fast forward this video. So in here I get step size, number of points, and rays in a given angle. Scaling will be a decision variable to be maximized or minimized. I will put the conditions that every matrix I get in a list of LMIs must be positive semi-definite. These will be the x and y coordinates of the ray that starts in the center and with an angle theta scales farther and farther away until it ceases being feasible. And then this optimizer with this LMIs condition, the ones in here, plus this scaling stuff, then it minimizes scaling, and if I do a two-sided option, then it minimizes and maximizes scaling with some options and whatever. And theta is an input parameter that ranges in, the angles, a grid of angles I wish in, and the output of the optimizer is the x and y coordinates of that point that maximizes or minimizes the scaling of the ray. So well, with all this and a lot of plot stuff, you can draw the shape. And how do I compute the analytic center? Well, I create a big block diagonal matrix with all the linear matrix inequalities, and I tell the optimizer to optimize with my LMI constraint, of course, that to optimize maximizing the geometric mean of the eigenvalues of that big matrix, and the geometric mean is the square whatever of the product of the eigenvalues. So this thing maximizes the product of the eigenvalues of this big matrix consisting of all the LMIs in block diagonal. So this optimization computes the analytic center we saw in the figures in previous videos. So this is a quick outline of the plotting stuff that, okay, you can download the code and inspect and play with it. And it's a very draft and careless code writing, so by no means I am claiming that this is the fastest or the best way to do it. So once we get this ray tracing way of plotting these LMI sets, what can we do with such sets? Well, we can do several things with them. First, for instance, if I have an LMI1 for a given LMI set and LMI2 for a given different LMI set, then if I put the same X in these two lifted, maybe, LMI sets, if this is feasible for X, Psi1, Psi2, this means that the LMI sets intersect. So for instance, we can think on, some kind of planning application or whatever in which objects must not collide and objects may be represented by LMI sets. So these collisions will amount to checking if they do intersect or not. We also can optimize linear things on them. For instance, the egg shape had some LMI, and then I can call the optimizers subject to these LMI constraints, optimizing x1 minus x2, let's say. Then I get this optimal stuff, and if I plot the egg set and this optimal thing, I get this, so that this is the optimal point, and this green line is sort of a tangent line in which x1 minus x2 is constant, and this constant is the minimum possible one. I am minimizing it. The maximum one, of course, will be over here, somewhere like here, so I can obtain this tangent point, these points that minimize or maximize a linear function over an LMI set, so that I can generalize linear programming, which is, on polyhedra, to linear programming on LMI sets and use LMI software in a reasonably fast and efficient way because it's convex optimization. The second thing I can optimize is a class of convex functions that are SDP-representable, the abstract thing of saying that, okay, if I can express my problem of minimizing something called T, subject to some LMI constraints on X or lifted additional variables eta, subject to, of course, X belonging to a given LMI set, then I can minimize things in LMI sets with this semi-definite programming software. For instance, as an example, if I have that X1 belongs to a LMI set S1 given by this inequality, X2 belongs to a given LMI set S2 given by this inequality, then I can express in this way, minimizing the distance t between x2 and x1, because this LMI means that x2 and x1 are separated by the distance less than d. So the minimum d, so that these 1, 2, and 3 LMIs is feasible, will give me the minimum distance between LMI sets. A particular example of this is made in another video, so I will stop here for brevity. Just as a last remark, there are things that we cannot easily do with them, at least with semi-definite programming stuff. Or well, maybe we can do it with some sum of squares, Positivstellensatz, multipliers, whatever, but okay. To check if one LMI set is inside another one. That cannot be done without extra tools, this sum of squares, Positivstellensatz stuff, but okay, for brevity, I am not discussing that extra tools in this video, in which we just conclude our first introduction to what LMI sets are, to what lifted LMI sets are, and how to plot them, and how to optimize some interesting things on them, or how to check if LMI sets intersect. So we end here. Thanks for watching.